In this lecture, we are going to discuss the difference between resistors connected in series and in parallel. Let's start with a simple circuit, having a battery with two resistors in series, R1 and R2. As discussed earlier on, the current in the circuit, capital I, is the same through all components. The battery's EMF, E, is divided between the other circuit components according to the ratio of their resistance. So, we know that the sum of voltages across each resistor must add up to the battery's EMF. Hence, E is equal to V1 plus V2. Now, applying V equals IR on each term, we get that the battery's EMF is equal to the current I multiplied by RT, which denotes the total resistance in the circuit. So here we are using the equation V equals IR with total values. So battery's EMF, current through battery, total resistance in the circuit. On the other hand, if we apply V equals IR on each resistor, we get V1, the potential difference across R1, being equal to I times R1. And similarly, V2 is equal to I times R2. So substituting each of these results in this equation, we get IRT instead of V is equal to IR1 plus IR2. That is, instead of V1 plus V2. The current is the same in each term, so it cancels. And we are left with total resistance is equal to R1 plus R2. I know that you are familiar with this result, but you must also know how to derive it from first principles. For any amount of resistors in series, we keep on adding the resistances with each other such that the total resistance for n resistors is R1 plus R2 plus so many resistors till the nth one. Let us now consider a simple parallel circuit with two bulbs. First of all, you must note that both diagrams are showing the same circuit arrangement. So please do not let the way a circuit is drawn to compromise your understanding of a circuit. In particular, you must note that both bulbs are connected between the same 2 points here labeled A and B. Okay, so in both diagrams, these are shown. Both bulbs are connected between the same 2 points. If we denote the terminal PD across the battery by capital V, then the potential at point A, that is the potential at the positive terminal of the battery, is plus V. Whereas the potential at point B, the negative terminal, must be 0. These are not potential differences, but potentials at points. So the potential at point A, I repeat, being the positive terminal of the battery, is plus V. Since the terminal PD across the battery is V, and the potential at point B at the negative terminal of the battery is 0. So this clearly shows that the potential difference, meaning subtracting potentials at points A and B, so here is V and here is 0, so the difference is V. So the potential difference across both bulbs is V. And this explains why components in parallel have the same voltage across them, irrespective of the number of components, which means that if I add a third bulb and I connect it again between points A and B, I will get again a potential difference across the third bulb of V. So we keep on getting the same voltage across each component added in parallel between the same 2 points. Now, the main feature of a parallel circuit is that it provides more than one path through which current can flow. For example, if we consider point A, which we call a junction, okay, these points are called junctions. We have another junction here, B. So here this circuit forks into 2 branches, such that the current supplied by the battery, capital I, so this is the current supplied by the battery at point A. What happens? It is divided between both lamps. So part through here, denoted by I1, and part through here, denoted by I2. And these currents obviously need not necessarily be equal, and that is why we are labeling them differently. Note also that if a switch were to be connected in series with each lamp, for example, a switch here or here, then it would be possible to operate each lamp individually. So that is another advantage of having connections in parallel. Now, at point A, the current in is I, and the current out is I1 plus I2. And we know that these two must be equal by conservation of charge. What does this mean? So the amount of free electrons approaching point A must be equal to the amount of free electrons leaving A, part through here and part through here. So we know that the summation of currents must hold. I is equal to I1 plus I2. Again, we are going to apply the result V equals IR at each term. So I being the total current through the battery, it is equal to the battery's terminal PDV divided by the total resistance in the circuit, RT, denoted RT as before. Applying the result on each component, we get current through bulb 1, I1, which is the potential difference across it, V, divided by R1, and similarly, current through bulb 2, I2, is the voltage V divided by its resistance, R2. Okay, so here we have R1 and R2, which are denoting resistance of bulb 1 and bulb 2. So we're saying that I1 is V divided by R1, I2 is V divided by R2. The battery current I is the same voltage V divided by the total resistance in the circuit. So, substituting each of these results in here, so instead of I can write V on RT. Instead of I1, V on R1, and instead of I2, V on R2. So I get this. V on RT is equal to V on R1 plus V on R2. V is common in each term, so this cancels, and we are left with 1 on RT is equal to 1 on R1 plus 1 on R2. And this is another result you should be familiar with from your previous experience in physics, that in parallel we add resistances via the reciprocals. We can rearrange a bit this equation. The working is shown here. So we can get this result. So if we arrange to get RT as subject rather than 1 on RT, okay, so know the difference, RT is subject, then the results reduces to R1 R2 divided by R1 plus R2. The advantage of having this result is that it gives you immediately the total resistance rather than its reciprocal. And this is easily remembered as product on sum. So total resistance for two resistors in parallel is their product divided by their sum. However, this result only holds for two parallel resistors, because if we have more than two, then we have to use the original result. So this is showing the result for any amount of resistors in parallel. So we keep on adding the reciprocals. However, you must be careful that the final result is not the total resistance, but its reciprocal. So you have to do the reciprocal of the final answer to get the total resistance. Now, it is important to note that whereas adding a resistor in series increases the total resistance in the circuit, adding a resistor in parallel does exactly the opposite. That is, it decreases the total resistance in the circuit. So I'm showing this here. Adding a resistor in series increases the total resistance. Adding it in parallel decreases the total resistance. And this might sound awkward at first, but the reason is that by adding a resistor in parallel, you are not only adding a resistor, but you are also creating an additional path for current to flow. You may see this clearly in the following situation, where we have any amount n of identical resistors in parallel. So if we apply the result, 1 on RT is 1 on R plus 1 on R plus, and we keep on doing this n times, so it is simply n times 1 on R, or n on R. But this is 1 on RT, so RT is the reciprocal of this, so R on n. And the result clearly shows that the higher n is, which is in the denominator, so the more resistors you have in parallel, the less is the total circuit resistance. For example, with two resistors in parallel, 10 ohms each, the total resistance between points X and Y is 10 ohm 2, so 5 ohms. On the other hand, with four 10 ohm resistors in parallel, the total resistance between X and Y is 10 ohm 4, so 2.5 ohms. So the total resistance is halved. To find the total resistance between 2 points in a given resistors network, we refer to such resistor configurations as resistor networks, imagine connecting a battery across those 2 points. So, if you are given a resistor network that is not part of a circuit, to find the total resistance between 2 points, imagine connecting a battery across those 2 points. Let's consider, for example, the following network of resistors, each of 6 ohms. The question is asking us to find the total resistance first between terminals A and C, and then between A and D. So, as we're saying, we start by drawing the diagram with a battery connected between A and C, which is here. Okay, so please appreciate that this is equivalent to this with a battery connected between here and here. Okay, so I am also adding points A and C to help you refer to the diagram given. Once you do that, then it is very much straightforward because we have 6 ohms and 6 ohms in series. So these two add up to make a 12 ohm resistor here. This is on its own, so it remains 6, whereas these two add up to 12. So we've reduced this network of resistors to 3 resistors in parallel, which is now straightforward to calculate because applying the result for total resistance in parallel, we get 1 on 12 plus 1 on 6 plus 1 on 12, which is 1/3. So the total resistance between A and C is 3 ohms. Then the second part is telling us to find the total resistance between A and D. So this is the original circuit given. So we imagine now including a battery between A and D. So we redraw the circuit. Okay, and you must be very careful here. So this 6 ohm resistor must be drawn alone across the battery, which is here, in between points A and D, just as here. Now, if we move from point A, here we have a junction where part goes through this 6 ohm resistor alone, and part goes through these 2 resistors in series. So, from junction A, which is the same as this point here, okay, part goes through 6 ohms alone. This is this resistor here. These two together form a 12 ohm resistor, which is here. These join together at this point, which is here, and then we move through the 6 ohm resistor to point D. So we move through the 6 ohm resistor to point D. From then onwards, it's pretty much straightforward because we have 6 and 12 ohms in parallel, which gives us 4 ohms. So I've redrawn this circuit to this, always simplifying. So I've got rid of these two in parallel and replaced by their equivalent, which is 4 ohms. Obviously, the other two, okay, are still there. But now I have 4 and 6 in series, giving me 10 in parallel with 6. So I've reduced this rather complex resistor network to simply a couple of resistors in parallel, which I can simply add using this result, which we've seen before. When having two resistors in parallel, it is simply product on sum. So 10 times 6 on 10 plus 6, which gives me 3.75 ohms. Now, in a different example, we're given two lamps, A and B, connected in parallel, and we're given the currents. The current through A is 20 milliamps, that through B is 10 milliamps, for a total current of 30 milliamps drawn from the battery. The battery has an EMF of 3 volts, and these 0 ohms here are showing that the internal resistance of the battery is 0. So its EMF, 3 volts, is equivalent to the terminal PD. The question is asking us to calculate the current through lamp A if B is switched off. So I've drawn the equivalent circuit here. So what is the current through A if no current flows through B? Now, at first, you might be tempted to say 30 milliamps. And this is because you reason out that the 30 milliamps originally drawn from the battery will now all pass through lamp A. But this is totally incorrect. And the reason is that the current through A only depends on the voltage across it, which was 3 volts here and has remained 3 volts here, and its resistance, which obviously didn't change just by flipping the switch of bulb B. And this is I'm showing here. So the current through A, I, is V on R. So V is 3 volts, the voltage across it, and this is the resistance of A. We don't know it, but whatever it is, this hasn't changed. So here I'm saying that neither of these values change by switching off or on lamp B. So the current remains the same, 20 milliamps. So what we're saying here is that only 20 milliamps are now drawn from the battery. And this makes sense because if both bulbs are switched on, then the total current drawn from the battery is 30 milliamps. But with only lamp A switched on, we should expect the total current drawn from the battery to decrease. And that is exactly what's happening here.